Pluto compels them to climb and drop as its circle crosses the way of one more planet at the most distant spans of our nearby planetary framework. Pluto, the confounding little planet, is producing a ton of fervor in the field of space science. Late improvements suggest that Pluto might actually crash into Neptune, causing disquiet among cosmologists and space devotees. Notable figures like Neil deGrasse Tyson and Michio Kaku have raised alarms about the potential outcomes of this celestial encounter. But how did Pluto end up on an impact course with its adjoining planet? Besides, what might this enormous conflict imply for life on Earth? Join us as we explore how Pluto's circle is converging with Neptune and why this peculiarity is leaving scientists concerned. Once viewed as a regular planet, Pluto underwent reclassification and is now referred to as a dwarf planet due to its abnormal orbit. Despite this downgrade, Pluto continues to captivate and interest the astronomical community. Recently, concerns have been raised by respected scientists, such as Neil deGrasse Tyson and Michio Kaku, regarding Pluto's trajectory, which may bring it into closer proximity to Neptune. This alignment suggests a series of potential interactions between these two grand celestial bodies, with significant ramifications for Earth. Pluto's orbit around the Sun is unique, distinguishing it within our planetary system. Its orbit is notably elongated, spanning great distances as it travels. Since its discovery in 1930, Pluto has yet to complete a full revolution around the Sun, which adds to its mystique. Unlike the more circular orbits of major planets, Pluto's path is highly eccentric, making it a distinctive entity in our solar neighborhood. The tilt of Pluto's orbit is another fascinating aspect, deviating 17 degrees from the ecliptic plane, giving it a sharper angle than the orbits of other planets. This combination of inclination and elongated orbit adds layers of complexity to Pluto's movement around the Sun. One particularly intriguing characteristic is its periodic interaction with Neptune's orbit. For about 20 years in each cycle, Pluto's path takes it closer to the Sun than Neptune's, defying expectations given the distinct locations of these two planets. Notably, Pluto's orbit is not circular but elliptical, leading to significant fluctuations in its distance from the Sun. At its closest approach, Pluto reaches about 30 astronomical units (AU) from the Sun, while at its farthest point, it extends beyond 49 Australian dollars, more than twice Neptune's distance from the Sun. Furthermore, Pluto's orbit is tilted at a critical angle relative to the major planets, adding to the intricacy of its path and interactions with other celestial bodies, particularly Neptune. When Pluto and Neptune do align in their orbits, their gravitational forces subtly adjust their trajectories over time. This complex relationship highlights the interconnectedness of celestial bodies, with each exerting gravitational influence over the others, shaping their orbits. Recent advancements in observational technology have enabled astronomers to track Pluto's path with unprecedented precision, offering deeper insights into its orbit and its potential impact on the stability of the outer solar system. While a direct collision between Pluto and Neptune remains unlikely, the possibility cannot be entirely ruled out, prompting increased interest and research from the astronomical community. Despite its small size and distant location, Pluto continues to command attention. So why hasn't a collision occurred between Pluto and Neptune? The answer lies in the gravitational interactions between planets. When astronomers first studied Pluto's orbit, they were puzzled by its unusual behavior. Unlike most planets which maintain a consistent plane as they orbit the Sun, the ecliptic plane, Pluto's path deviates sharply, adding another layer of mystery. The real enigma arose when scientists realized that Pluto's orbit crosses Neptune's path. Yet, despite this strange overlap, Pluto's trajectory remains stable, demonstrating the intricate mechanics of space. Understanding how celestial bodies like Pluto, Neptune, and the Sun interact gravitationally is a challenge for astronomy. Predicting the motion of these bodies is akin to determining their future positions based on their initial conditions and the forces they exert on each other. For Pluto, the relationship between its orbit, Neptune's orbit, and the Sun's gravitational pull creates a delicate and coordinated system that keeps Pluto's path predictable. Terms such as precession, libration, and VSOP variations help researchers navigate these complex dynamics. Understanding these principles is crucial for maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains about 90 degrees away, preventing a direct impact. The phenomenon of libration ensures that Pluto stays safely out of Neptune's path, even when it approaches. The VSOP variations, named after researchers von Zeipel, Poincaré, and others, explain why Pluto's orbit may appear irregular yet remains predictable over time. Despite the apparent chaos of space, specific patterns and principles help keep objects in orbit. These mechanisms stabilize Pluto's trajectory, mitigating the risk of a collision with Neptune. The sensitivity of orbital mechanics highlights how even small changes in a planet's position or velocity can lead to significant alterations in its path over time. Using complex computational simulations, astronomers can model Pluto's movement in space, observing how slight variations in initial conditions can drastically modify its orbit. In the late 20th century, these simulations revealed that while Pluto's orbit appears stable, it is subject to chaotic fluctuations. Even minor differences in Pluto's starting position or speed can lead to massive changes over long periods. However, Pluto's trajectory has remained largely stable for billions of years, suggesting that despite its apparent instability, its motion follows a discernible pattern. Nevertheless, predicting the behavior of planets with such unpredictable orbits remains a challenging task. These systems are so complex that long-term forecasting becomes difficult. Simulations help estimate potential outcomes, but they also highlight the inherent unpredictability of these celestial movements. Gaining a better understanding of Pluto's orbit is crucial, particularly when assessing the likelihood of a future collision with Neptune. This knowledge helps us understand how our solar system operates and reminds us that even seemingly unstable orbits can be governed by gravity and the broader mechanics of space. Exploring space unveils many surprises, and Pluto's orbit serves as a prime example of such phenomena. Unlike the orbits of other planets, Pluto's path around the Sun is more oval-shaped, meaning it does not form a perfect circle. At times, Pluto even ventures closer to the Sun than Neptune does. This creates intriguing dynamics, especially since Neptune is also moving along its own trajectory. While the probability of Pluto and Neptune colliding remains low, it is essential to recognize the forces at play. Gravitational pull acts as an invisible force, keeping the planets in their orbits. So, although Pluto and Neptune may appear to be on a collision course, their paths are meticulously shaped by gravity. Studying Pluto's orbit provides valuable insights into the delicate balance of forces that govern space. What may initially seem chaotic is often the result of a finely tuned system of gravitational interactions. Ongoing research and observation are essential for expanding our knowledge of space, particularly regarding our solar system. Imagine the implications of a collision between Pluto and Neptune. It would be a pivotal event, reshaping our understanding of the outer solar system. Although we have made significant progress in space exploration, such an event would highlight the vast gaps in our knowledge, signaling the need for further study and technological advancements. Further examination, by zeroing in on what bigger planets mean for Pluto's circle, researchers can uncover imperative data about the developments of the whole planetary group. It reveals that the positions and movements of planets can influence the paths of other objects in space. Despite the complexities of the universe, the possibility of Pluto crashing into Neptune remains a concern for cosmologists. This raises the question, why might such a collision occur, even though it seems improbable? Neil deGrasse Tyson, a prominent astrophysicist, has shared his thoughts on Pluto's renaming. He believes renaming Pluto as a dwarf planet instead of a major planet like Earth is a step in the right direction in our understanding of space. Tyson argues that we are continuously learning about how objects travel through space, and Pluto's strange trajectory is a clear sign that there is more to discover. He finds the mysteries of space fascinating and believes that events like Pluto's renaming engage the public in the pursuit of space science. Tyson works alongside other experts to warn about the potential risks of Pluto's orbit, particularly its possible collision with Neptune. He suggests that such an impact would be a grand event for the entire solar system, with consequences that could ripple across the universe. A collision between Pluto and Neptune would release massive amounts of energy and could cause Pluto to break apart, sending fragments tearing through space, possibly colliding with other celestial bodies. Even Neptune would be affected, with its orbit altered due to the impact. Michio Kaku, a well-known theoretical physicist, offers his own perspective on the relationship between celestial mechanics and space exploration. Kaku emphasizes that studying Pluto's orbit can provide critical insights into the future of space exploration. He believes that understanding the complex gravitational interactions between celestial bodies like Pluto can improve future missions, helping us navigate the solar system more safely and predict potential dangers. Kaku's work in theoretical physics, particularly in string theory, aims to decipher the fundamental laws governing the universe. He proposes that by studying the dynamics of celestial bodies like Pluto, we can unlock a deeper understanding of the forces that shape our cosmos. Both Tyson and Kaku agree that observing events like a potential Pluto-Neptune collision offers an exciting opportunity to learn more about the universe. In particular, such an event could have significant implications for our understanding of string theory. String theory seeks to explain the fundamental forces of nature by modeling the universe as a series of one-dimensional strings. A Pluto-Neptune collision could create extreme conditions that would provide valuable data for testing string theory's predictions about spacetime. While the immediate impact on Earth would be minimal due to our distance from the outer solar system, the scientific knowledge gained from such an event could be groundbreaking. It would expand our understanding of the fundamental nature of the universe, pushing the boundaries of theoretical physics and astronomy. As experts continue to study the gravitational effects of neighboring planets like Neptune, the dynamic and ever-changing nature of space becomes increasingly clear. However, space remains full of mysteries. The three-body problem, where multiple celestial bodies exert gravitational influences on one another, is just one of the many complexities that scientists are trying to solve. The ongoing exploration of space is crucial for broadening our understanding of the universe and the laws that govern it. Although the likelihood of planetary collisions is very low, the possibility still exists due to the influence of gravitational forces. These forces can alter the orbits of planets, potentially leading to collisions over time. One example of this phenomenon is the TRAPPIST-1 system, which contains 7 Earth-sized planets. The gravitational forces between these planets can create orbital resonances, making their orbits less stable and possibly leading to collisions in the future. Researchers are closely monitoring these systems to better understand how celestial bodies interact and how planetary paths can shift. In addition to planetary interactions, rogue planets that no longer orbit a star can drift through space. These planets, which were once part of a star system, can travel vast distances and occasionally pass through other star systems. However, the vast emptiness of space means that the chance of a rogue planet colliding with another planet is low. Despite their rarity, rogue planets are intriguing subjects of study for astronomers. Ultimately, when galaxies collide, the gravitational forces involved can alter the movement of stars and planets. While planets may not collide directly, their orbits can be disrupted, potentially ejecting them into space or causing them to collide with other planets or their host stars. This disturbance can lead to the formation of new celestial bodies or even the birth of new stars. The late heavy bombardment hypothesis suggests that around 4 billion years ago, an increase in impacts from comets and asteroids occurred, likely caused by the movement of the outer planets like Jupiter and Saturn. These impacts disrupted the orbits of smaller objects in space, many of which were ejected into the inner solar system. Although these impacts did not involve direct planetary collisions, they serve as a reminder of the power of gravity to reshape the paths of objects in space. The late heavy bombardment hypothesis is a fascinating concept that suggests the early solar system was subjected to intense cosmic bombardment. During this period, the outer planets, such as Jupiter and Saturn, are believed to have undergone significant migrations, displacing many smaller objects and sending them on unpredictable trajectories. As a result, these objects collided with the inner planets, leading to significant impacts. While these encounters did not involve direct planetary collisions, they influenced the surfaces and compositions of the planets, particularly Earth. It is even believed that this bombardment may have played a role in delivering essential elements, such as water and organic molecules, to our planet, contributing to the conditions necessary for life. These impacts, which occurred billions of years ago, are a stark reminder of how gravitational forces from larger bodies can disrupt the movement of smaller celestial objects, altering their orbits and trajectories. In this case, the powerful gravitational influences of Jupiter and Saturn were instrumental in shaping the course of many objects that ultimately found their way into the inner part of the solar system, further complicating the delicate balance of forces at play in our cosmic neighborhood. The effects of these early cosmic impacts can still be seen today in the craters found on the surfaces of planets, moons, and asteroids. Such events highlight the complexity of space and the fragility of planetary orbits. Just as Pluto's erratic orbit raises concerns about the possibility of a future encounter with Neptune, the broader historical impacts of cosmic forces help scientists understand how planetary systems evolve over time. The idea of celestial bodies colliding or influencing each other's paths serves as a reminder of the dynamic nature of space and the potential consequences these interactions may have on life within our solar system and beyond. The delicate interplay of gravitational forces is also exemplified by the concept of the three-body problem, a classic dilemma in physics and astronomy that describes the difficulty in predicting the motion of three celestial bodies that influence each other gravitationally. As we observe the interactions between planets like Pluto, Neptune, and others in our solar system, we are reminded of how challenging it is to predict long-term orbital paths with certainty. Despite advances in computational simulations and observational technology, the precise movements of these bodies remain elusive, especially when considering how even tiny variations in speed or position can have significant effects over long periods. Additionally, researchers remain vigilant about the potential dangers posed by rogue planets, celestial bodies that no longer orbit a star and instead drift through interstellar space. These planets, ejected from their original solar systems due to gravitational disturbances or close encounters with other stars, present a unique challenge to our understanding of planetary dynamics. While they are rare, their presence in the universe highlights the unpredictable nature of space. Over time, rogue planets can travel immense distances, sometimes approaching other star systems. Yet, the vast emptiness of space makes direct collisions with other planets or stars highly unlikely.